Thank you to the user group for allowing me to give you a glimpse about around building native images with Spring and GraalVM. I'm Dan Dobrin. I'm based in Toronto. I'm an architect with VMware. My focus was over time, like building high-speed frameworks. I worked on different projects. I'm too old to remember about them. Right now, I'm helping clients build a fast application, transition their applications to microservices, kind of like bridge the gap between a platform and a running workload. So what we want to talk today is, we hear about like native images, and the entire focus is on, in the industry today, on a simple equation. If I have a faster startup and I consume less resources, I have better cloud economics. So when we look into this, we're always thinking like, can we do this like simple, seamless? And that's where we're striving to get to. But sometimes maybe things don't work like that. And we want to look a little bit under the hood and see what can trip us up. That's the focus of what we're doing. It's complementary to what you hear in different presentations, where you would hear about the benefits of native images, what it takes to get there, how to build them. However, as this is a maturing technology, we have to be aware they're not necessarily problems, but there are steps on the maturity scale. So allow me to share a screen. I'll share my Mac screen. I hope everybody can see that.
Yep, you're looking and sounding good. You're fine.
Okay, thank you. So let's get through it. So what are we trying to talk about today? So we're trying to compare for a second, as a recap, just in time with ahead of time compilation. Then we want to focus on a number of areas, like understand build time class initialization for native images as it compares to runtime initialization. Limitations of ahead of time compilations. What do we need to know, and how is Spring Native going to help us mitigate them? What's working differently for some of Java's features in native images? And along the way, can we learn to write better code in the process? So before we get through a little recap of the building blocks on the road to native images, let's try and run a little sample and see where we're trying to go. Spring Native, running on top of GraalVM, is trying to help users move applications, build native images from JVM images unchanged. So let's see if this is actually doable. So if I'm starting a native image, you're not really going to see me building native images because they take quite a long time. That's why we offload them to CI/CD processes. So I have the images pre-built, but we can run them. So this is the Spring Native. This is the Spring on JVM. It took like 2.4 seconds to start. Not ideal, but this is what we were used to. When we're going to native images, suddenly this starts in 90 milliseconds. And we see right away the first benefit: super fast startups opens up a myriad of possibilities. The same application, is it up and running? Yes, looks good. However, was this a seamless transition? What if I pick an intermediate image and I'm going to start this? This tells me that something actually went wrong. So this is what we're trying to understand. It's not necessarily what went wrong, but what did we have to do to move from a JVM image to a native image? So put our pets aside for a second and come back and understand where is my PowerPoint? Okay, so I think you can see this. So how do we compare just in time versus ahead of time? So in traditional Java application, Java code is compiled by the Java C program in the SDK into Java bytecode, which we're going to package into a jar file. Then the JVM uses a bytecode interpreter to execute a program in the jar on the host platform. So when the code is interpreted, the execution will always be slower than the execution of the same program compiled into a native image. And this problem is mitigated over time by just-in-time compiler. The hotspot technology will help us translate into native images the code with the errors of the program which are executed more often. So performance improves as we go along, and we execute different passes in the program. Now, ahead of time has the same type of approach. We take the Java code, we compile it into class bytecode, build our jar archive. But now we're taking a different step. We're going to build the native executable for that application ahead of time. That means before we run this. By doing this, the application will not require any kind of JIT compiler, and it will start and run almost instantly on that native runtime because the machine understands that. One immediate benefit, if we think about it, native images don't depend on the number of CPUs at startup because the JVM needs to interpret code, but the native image does not. So we see fast startup, we see how fast our pets are. We can think that we need already less resources. So this starts looking actually pretty good. So what are some key differences between JVM and native images? So native images are different from JVM apps. We're making some closed world assumptions here. There's a static analysis of the app at build time. We start from our Java main, and we require a number of things. So we require some upfront configuration for dynamic Java language features like proxies, reflection, resources. The class pass is fixed at build time because we need to know ahead of time everything we need to build that image and to run it. There's no lazy class loading. Some code will run at build time, and there are no runtime optimization. The first request executes as fast as, I don't know, number 100,000. What is it built on? So the GraalVM, the basic idea, it's a virtual machine that can execute a whole lot of languages, maybe not all, but all the common ones which we're going to use. And when the GraalVM project was started by Oracle was thinking, do I need the entire JVM? Well, no, because the native image does not need to include the full JVM. It has a purpose-built different runtime system, and it includes only the necessary components, memory management, thread scheduling, GC, in a component called the Substrate VM. So this is interesting. So let's think a bit what is actually happening. So the tool transforming our code into a native image is called native-image, literally. Usually, what are we accustomed to when we build a native image? Well, we have generally a JDK, a VM where we're going to run, the code we need, all the dependencies, we build them and we execute them. But when we want to transform them into a native image, we have this three-step process. We will undergo a comprehensive static analysis and we'll process all the classes of an application, all their dependencies, including those from the JDK. It will statically analyze the data to determine which classes and methods are reachable during that application execution. And then it will write them into an intermediate model. This reachable code and data will be then compiled ahead of time into a native executable for a specific OS and architecture. Now, in the end, we end up with a binary, which has two parts. One is the compiled code that we can understand, but there's also an initial heap, which is taken via heap snapshotting. So let's understand why. The code part, this is easy to grasp because this part contains all the classes and methods that need to be included in the image because the static analysis found a possible code path to them or their inclusion was pre-configured. The image heap, on the other hand, is a concept a little bit more unfamiliar for many developers. If we think that a native image build process, if we think of it as running your app for a bit, initializing some necessary classes and their data, and saving the state of the application for future use. Then when we move into a test environment, a performance test environment or production, this initialized state is already prepared to use, and we can load it right away, and we don't have to load these classes. How do we understand how we can see what is in the code heap or the image heap? There is a dashboard which should help us. Now, if you see, these are several layers, but in the end, we end up with one single binary. How does this actually look like? So if we use dive and start two images, this is on the left, my pet clinic on the JVM, on the right, a native image. So we have a Linux distribution at 60 megs. And as we go through the layers, yes, these are built with cloud native build packs. And unfortunately, there's an issue here. It won't print the created by for the layers, but we can navigate through them. We can see the JRE, and it clocks in at a fairly sizable, it's a Java 11 at 144 megs. And this is fine. But then as we go along, we see also all the dependencies, my Spring Boot, my Log4j, whatever the pet clinic needs, the Hikari connection pool. And in the end, my application is only 1 meg. So I can see here by this lifecycle launcher in the image that this was a Spring Boot executable jar. When we're in the native image, we can use a highly optimized distribution. This is only 17 megs. Because it requires only the minimum to run a native image. And all we see here is the application image. Yes, it builds everything, Substrate VM, all the classes which we will need to run pet clinic at runtime. So you can see a massive difference in terms of sizes of our images. So if we come back to our native image technology, let's think a little bit of how we get to this configuration. So the native image builder cannot figure all the execution passes if some language features are fully dynamic. So there's a build configuration is required for which will inform native image which class and method to include. You can do that manually, which is tedious, or you can run a tracing agent in GraalVM, and the configuration is stored in a subfolder, any subfolder of meta-inf native image on your class path. But you can also use Spring Native. Spring Native will bring Spring Boot native application support. So it will analyze the Spring Boot application at build time. It will compute the most optimal native image config, and it will auto-generate the configurations for developers. It will do the heavy lifting for you. Along the way, it's looking at some build time transformation for an optimized footprint and for compatibility for JVM images. The way Spring Boot looks at it, it's not just to help you build efficient and optimized Spring native images, but also at how this technology could help you could be actually reused in Spring Boot or the Spring framework in the future. So it's a dual purpose here. Spring AOT is a general purpose framework which Spring Native uses for code analysis and generation at project build time. So this is not a native image build time. This is just a regular project build time. It will generate code to represent what is configured in Spring factories, which are all the classes which would have to be loaded via reflection. It will optimize away anything aggressively that is not required. Let's say if we have conditional on class or conditions on different or similar conditions, those won't pass, they will be discarded. It will generate for you configuration for later use by native image. It is being extended by many other projects in the Spring ecosystem. Spring Data, for example, very popular. And in the end, we have to think about that. We see two benefits. One, we can push some code from startup to build time. From startup time to build time. So before we even build our, before we even run our image, we can at build time push some code. And if this code uses Java construct, Java language construct, like method references or lambdas, rather than reflection, then the native image static analysis understands the system easier and produces more optimal images. Compare that for a second to the JVM. JVM loads everything and discards afterwards, whereas Spring OT and Spring Native, based on and running on Graal, will just include what is actually required. Now, does ahead of time have any compilation limitations? I wouldn't call them necessarily limitations, but dynamic features or different behavior, which we have to understand as we're moving into this new and optimized world of native images. So what do I need to know? And this is kind of like the focus of our discussion this evening. It's very important to understand for native image compatibility and optimization aspects. I group them into four. Maybe other people see it differently, but can any of these trip us up? So what are they? So class initializers, the distinction between build time initialization and runtime. We need to have a good understanding of it. Then how do we generate configuration for dynamic features, and what do we have to provide? While we explore these two, we have to recognize two things: that there are some features which are incompatible with closed world optimization, but there are also features which might operate differently in native images. So by this, can we actually improve our coding? Or if we're moving older application running in the app server world and we think that, oh, this was working fine at that time, if we decompose a monolith and now we build microservices or functions, is the operation of those code snippets the same or not? So let's take them one by one. So runtime versus build time initialization. So all class initialization code, static initializers, and static field initialization for the app is executed at image runtime by default. Now, the native image builder will allow us the choice of which parts of the app should be initialized at build time or which should be at runtime. Not everything is amenable to this split, but let's understand how we can do it. Now, you can control it via native image options in Graal, or using annotation-based initialization hints. And I'm sure everybody's familiar with annotations in Spring. So who can benefit from this? So class initializers for static and static final fields. Now, some static fields get initialized to run independent data. So we said it's not just code, it's also data. Let's say enums. Enums are objects, but they carry data with them. If we compare that with the runtime initialization, there are some performance implications at runtime initializations, because each time we have a runtime check before a static method called or field extra allocation, we have to say, has this been initialized? Has this been initialized? So who is using initialization? You're very familiar with all of them: Spring, gRPC, Redis caching, Jackson, SLF4J. So if we're looking at initialization, why don't we just take one sample? So let's take our class initialization sample here. And here we have a class which will access this public static second variable, and we'll create an instance of the second class where we're going to declare this constant. So we can think about this, that this should be actually running just fine. why would we expect that this is happening? Because this is a constant, it is known, and we can build this image. But let's try and run this for a second. If we run this, we don't want to run this. I said I'm not going to run any images. So let's run this failed one. What do we see right away? And we see a nice error right away. What happened is this char set could not be loaded. Why could it not be loaded? Because it's not a default loaded char set. This is a non-standard one. So my image builder did not understand this. It understood char set, it loaded the defaults. So here's a problem. Now, how can we actually address this? Well, we could put a flag. Graal has here a handy flag, but let's try to understand what is actually happening. And let's see if we can run if we can change this. So first, we're going to run some tests. And this test has failed. What did I just run? These are not the regular tests. Last Monday with Spring 0.10 and the release of a new project, GraalVM build tools, we can now build native images for JUnit tests. This is a major step. It's one of the 2 steps which came out last week, and I had to change all the presentation because some samples were a lot more interesting now. If we write our test and build this special test image, before we even build the actual image, we just run the test as a native image. If we have 100% coverage, we're ensured that our native application will run fine. So what should we actually do here? This is a Spring application, so we decide to enable this native hint. This is for our second part. And we're declaring, here's the first class, the second class, and initialize them at build time. So if we do this and we build our test, building a native test takes as long as building a native image. So we're going to skip this process. But once you build them, you can run them over and over again. This runs fine. What happened? The hint has generated for us the configuration, and it has generated for us the configuration, and we can see here that classes, if we search for it, the first and the second class have been generated. So this actually seems good. So once we run our application, we can see that everything is fine and this runs fine. Should we have added the flag? No, because maybe that flag is good once you have a good understanding of the entire initialization process. However, as we learn and go through these things, we need to see how we can troubleshoot and how we can go through these problems. So coming back to our application, we need to understand a number of there are some properties of initialized classes, some allocated to build time initialization, some to runtime. So all the classes which now have been initialized at build time are going into the image heap, and all of them in the image heap must be initialized at build time. I'm kind of like stating the obvious. But all the super classes and all the classes which could be initialized on the past must also be initialized at build time. So the code reached through the class initializer of a build time class is marked either as build time or rerun. So build time internally by Graal is marked that the class is initialized at build time. All of its static fields that are reachable are saved in the image heap. Rerun is an internal state, which means build time by accident. And we're going to have to avoid this because this is one of the problems which falls in the last category, things which work differently and they could trip us up. So these static fields will be evaluated at runtime. The other side of the coin is runtime initialization. Now, all subclasses of a runtime initialized class must also be a runtime class. Otherwise, the initialization of that class would also initialize the runtime classes and things would trip up. So runtime initialized classes cannot and must not end up in the image heap. Now, as we have this clear understanding, we have to see that there are some limitations of heap snapshotting. So not every object can be stored in the image heap. So for example, I group them again in 4 categories. Objects, and the top category for these 4 is objects retaining state from the build machine where we have built our native image. One thing would be open files. So we cannot write a file descriptor into an image heap when we're going to run the native image somewhere else. Running threads or continuations in functional programming cannot be stored in the image heap. Objects pointing to native memory, so let's say a map byte buffer. And in the end, this is the danger category. We could leak inadvertently build time information into the native executable. So for example, username and passwords, home directories, known random seeds. Generating a random seed and having it stored in the image heap is a recipe for disaster. So this is hard to prove if they end up in the image. So let's come back to our sample for a second. If I'm changing the application for a bit, and I'm going to uncomment this part. This will start the thread. That's fine. Let's move this zoom. And we're going to run our application. What are we going to see? Well, the same char set loader, but we're going to see this thread sleeping for 10 seconds and then say, well, I am done. So this is actually fine. But when we will move now and build a native image, we're going to say, well, let's take this. We leave these hints. We ran them before. Now we're going to run our application. It builds, but when it runs, we observe something. We see this print, but the thread execution did not occur. There's no error message here. So we have to know this, we have to recognize it and avoid this. So let's not run threads in and have them being initialized at build time because they are just not going to be written in the image. So what should we do in this case? So in this case, we have a simple option. We're going to set up the hint in a different way and say, well, the first class actually should be going at build time, at runtime, and the second class at build time. So we're splitting the two. By instructing now Spring Native to generate the right configuration and running our application, the Java application runs as fine as it ran before. That is not going to be a problem for us. But when we run now the application, and we build an image, we can see that this builds fine because one class addresses our need for build time initialization and the other one for runtime. So we see this, and this is actually fine. Now, coming back to our images, and let's park our pets. We see that there are also limitations here. But let's think a little bit. What if we have features which could create us problems? So let's take this sample for a little bit. And let's look at a different sample. What should this sample do? It will load Jackson, it will read this config file, and when it reads this config file, it will print out the values in this config file. So when it prints this, it will just show us the values which it printed. So this, okay, fine. But then we're thinking, can we improve our code? Can we actually, if we need Jackson only at startup, and this takes us 2.9 megs roughly, why should the image be almost 3 megs larger? Can we do something? So how about we move this code into a static block, and when we build it, we're going to, I play around with the POM files to say what I'm going to instantiate. And when we run this, we're asking for this class to be initialized at build time. If we do this, then, and we don't use Jackson anywhere else, then this is great. This class has been loaded, has been built into the image, it has been used. And then once we run it, this is not going to create us problem. It will actually bring us benefits. So this is reading some configuration, and we'll just fork off some threads and run. One, it executes faster because it doesn't have to go through Jackson initialization. But the other thing is the image is actually smaller. So how should we get to this idea that we can move some code around and improve our the way we build apps? There is a handy tool here, and this tool is a GraalVM dashboard. Should you use it on an ongoing basis? Not after each build, but when you're analyzing an application, architects, senior devs will look into it, and they would try to understand what are the low-hanging fruit, what could I potentially optimize. We can run a flag dashboard all, and that would allow us to collect this image. Please be aware that it would actually slow us down even more. So it will tell us the code breakdown and the heap size breakdown. Very simple, we discussed about them. So if we take the larger image, what do we see? The biggest culprit, and that's what gives us the idea to move this code, is are the Jackson libraries. And then the next thing would be our application. If we look through our application, we can drill down through it, but we can see Jackson taking up a lot of space. You see, in the end, our application, quite tiny. Here's our multi-threading app. Here's our main, and that's fine. So what should we do? We're trying to change this. So once we build the image again, and we have changed the code, we can see that now suddenly Jackson is not there anymore. So this was built at build time. It's marked as being built as build time. We asked for it, and we think that we did a very good job. And this is actually true, as long as we don't use now Jackson later, because that could create for us a problem. This is our application. We see our multi-threaded app, and we have improved our application quite significantly. Now, if we come back to our app, let's take this sample. Let's split this a bit and forget about running threads. Here's the same app. And let's say this is a config sample. So we call it config samples. We'll read this app. We'll load this. This is running fine. And we're going to run our application. And it loads fine. It says, yeah, I'm still loading the same threads and so on. That's cool. So what could actually go wrong? What if this code is written in a separate library or a separate method? Maybe another developer doesn't know that or doesn't see that, or we forget about things. So we ask for this class to be loaded at build time, but we also loaded Jackson. So we loaded it, we discarded it, and this class is loaded at build time. But then we make the mistake of wanting to access this at runtime, and we want to write the file back. I know these are artificial samples, but very good for things happening like this. I saw this by changing one of my samples and not understanding why this is happening. What is actually happening here? So when we actually run, we are going to see that our app will now fail. And our app will now fail, and I think this is probably the only one which we want to run. We want to build our application, and we're expecting now our application to build. However, we would see this fail. And why will we see it fail? Because it will get confused. And this will take, you see, even running a simple app with what I'm having just one class. I'm hoping I initialize the right one. And run this. We would see this. Image failing. Now it will build our test. So let's always be very clear of what we do. We ran our app. We wanted that class to be initialized at build time, but now the message is, well, the object mapper was unintentionally initialized at build time, and now this class wants to be loaded again. That class that should be initialized at runtime got initialized at build time. So now it gets into this confused state, and it creates for us a problem. So we should be very careful about these things. Now, if we look at our presentation, we said that we might leak build time information into the native executable. So what can actually happen here? So let's think a little bit. We take this class. In here, we're going to load some system properties, and we're going to run them, let's say user home. Happens many times in applications, or we load a private key. Many times these were happening in the old app server days, and errors like this happen then, it can happen now, they can happen now. Or we're going to build a simple random number generator where we use the time as a seed. So what can go wrong here? If we are asking and we're building this, we're enabling this class, if we're building this image and we're asking for this class to be loaded at build time, the values will be written into the image heap. So if I'm taking this app and I'm just going to run it, what will I see? Well, I will see a random sequence. I will see a private key and a time. But if I run it again, I print the first three random numbers. Let's run it again. We see a different random number. Okay, and we loaded this by mistake. It's always the same. Now, but we see a different random number, and we're thinking, okay, this is actually going to run fine. However, when we are going to run our application, when we're going to run our app, we want to build also, where is my sum? we see the app running, and it will always build for us. It will always build for us the same. It will generate for us always the same number. Why? Because this was running as a native image, and those values have made it. Into our image. Okay, so that's the one. Each time I run it, I'm going to see the same random number starting with 6081, 4225, always the same. The time changes, but the time can change, but the value stays the same. It's not easy, but somebody could actually get into our application and figure this out, and we have opened up a security problem. So what could we see here from all our categories? Yes, it's very beneficial to us. We can have size reduction, faster startup, but we have to be mindful that there are problems potentially in our code. Some we have to be aware that they work differently in native images, and others could lead to different security problems. Now, the second major category, class metadata features. So dynamic features in the language will require a configuration at image build time for closed world optimization. We live in this closed world optimization world now, and we need to know upfront of everything that is happening, but there are dynamic features in the language. So some are JDK features like dynamic class loading, reflection, JDK dynamic proxies, serialization, resource access, JNI. And we have also class proxies. Classes where we proxy an existing class where we don't have an interface. So that's why I'm creating a distinction class versus JDK dynamic proxies. Where are these used? We're going to see that, like AOP is one of the first would come to mind. So let's see who's actually using these features. So dynamic class loading, Spring is evidently a good example of using it quite effectively and extensively. MySQL, Postgres, Rabbit, different applications, which were, or many or most of them were using them on a day-to-day basis. JDK dynamic proxies, like Spring uses them, MySQL, Kafka, Rabbit, different applications as well. Then we have serialization. So serialization, I know serialization is recommended in general to maybe be used less. However, it is still pervasive in many applications from Spring projects, but I picked also the Quartz scheduler. Quite used for a number of years. Then we have resource access. Again, who will use resource access? Spring projects and all the data related projects. So when we would think about it and look at serialization, let's come back to our original sample. Our original sample was Pet Clinic. So we ran Pet Clinic, and when we ran Pet Clinic, was actually Pet Clinic running unchanged? No, because we could see that error. So what happened actually? What did we have to do? So there are like two things. We run some tests, and we have a vet test. So here we create a vet in the Pet Clinic, and we set some values, and then we serialize it. What did we say? That if the vet is loaded, regardless if it would be loaded at build time or at runtime, the vet and all its base classes should be loaded in a similar manner. However, for serialization, we need some configuration up front. So what should we serialize? So if we look at the vet extends a person. So the person extends a base entity. So these are the classes which we need to load and for which we have to provide the serialization hint. How do we do that? We will set up a serialization hint. And in the end, it also requires a number. So we have to list all of these classes so that this serialization hint will generate the right configuration. Now, if we think about resource access, let's think about it that by default, the native image builder will not integrate any of the resources which are on the class path during the generation of the final image. So Java localization support, very much used through our applications, will enable the Java code to load localization resources and show the right user messages suitable for the runtime settings in which you, and let's say your time locale or the format and so on. Now, in the native image needs ahead of time knowledge of the resource bundle your application needs so that it can load and store the appropriate bundle for usage in the generated binary. So we have two choices. We can provide a resource hint for our messages, and here's our resource bundle. Or we can do something else. We can create by hand one of the generated config files, and this is a resource config where we will declare this bundle. I'm using this example just so that you can see that maybe we just want to create this resource config by hand, and here's one of our alternatives. By making these two changes, we have now the ability to run Pet Clinic very nicely, and there's not going to be any kind of problem. Now, as always, how do we get to this understanding? We can always run our native tests. Very handy, and it could tell us how each test ran. And as well, we can run fail tests, and we can understand why they failed. Well, why did they fail? Because serialization failed, and we have the vet and the base entity. As we go along, it helps us. We get very nice feedback from Spring Native, and we will see right away, okay, I'm going to take these and create my hint. Now, a new category which came up last Monday, literally with 0.10 of Spring Native, is our class proxies. So class proxies will help us proxy an existing class for which we don't have an interface. So who's using it? Spring AOP, Spring Security, if we use like a pre-authorized annotation, Spring Batch and Hibernate. Generally, classes not implementing interfaces. So if we want to see how class proxies help us here, let's take a little sample. So we take an application, we have a controller, which will say here we have a class of controller where if we access the with endpoint, it will be okay. This is with a proxy, and the controller 2 is without a proxy. So now we're going to declare we want to build an aspect. So we will declare a point cut at this join point. What are we going to say here? That whenever somebody calls the person controller and that demo, please create a class for me, proxy the person controller because I declared a round aspect, and implement some logic. I can do things before I invoke the actual class. After, I can decide maybe I just don't want to invoke it at all. So we want to see this running, and to see this running, let's bring let's bring our little browser here. So as we run the application, we have not declared yet a proxy. We have not declared a proxy here. If this would be, if we don't provide the hint and build the image, and many times when you start, think about this, just let everything initialize at runtime and let's run it. And let Spring Native help us with information. When we run it, it will tell us like, oh, okay, so there's a class proxy missing at build time. So what was actually happening? So what was actually happening? It says there's a class proxy missing at runtime, and there's a hint which is required. So please add this actual hint. So we see this hint right away. Very handy for us, easy for us to find out. Sure, it will take us a few, maybe like a minute until we get to this error. And then all we have to do is we copy it, and this would be great. We observe it, we copy this, and then we're saying, okay, fine. Now we have this, and let's build our image. If we build our image, so we added a hint. We think, well, this is what Spring Native told us. But sometimes there are things which, as this is an evolution, and this technology evolves very fast. I picked a sample so that you can see that a hint sometimes is not enough. So sometimes we need to do more. So when we are trying to understand this, what should we actually do? So what happened here? What happened here is our application was actually not, it was missing the initialization of AOP. So, well, this is actually making us think, is there a way for us to address it? So let's think about it. What did Graal provide us at? What did we say that Graal provided us? Graal gave us a tracing agent. So that tracing agent, we could run the tracing agent and understand whether there is somewhere a delta or a missing part of what Spring generates in terms of configuration and what the tracing agent would help us do. So all we have to do is we have to enable this configuration. We will say now, don't build a native image. Build a native image, but run the agent for me. And when we configure the plugin, we're going to specify where this output should happen. And then we can compare. This is very, very simple. When we run it and it will build the config, we will see what Spring AOT generated. These are the config files. And what the tracing agent did. And we can compare them, and we're going to find a small problem here or there, and this is the delta. What actually failed is these two classes which have been added, and they should not have been. Now, again, this is not an idea of highlighting a failure. It's the idea of showing how quickly this evolves. So what is our solution to this? We're simply going to merge the two files. In subsequent versions of Spring Native, this will happen automatically. Right now, you just have to do a simple file merge. And now that you did it, you're not going to want to run this agent over and over again, because this would slow us down a bit more. We're just going to take the merge file and put them into our application under resource meta-inf native image and run our application. We build it and we run it. So let's run this. Okay, and let's bring our app. Zoom keeps popping up. And we're going to see this without the proxy. And if we run it with, it says this is proxy. So you can see I ran this. Spring Native told me right away, please add this hint. I'm adding this. Okay, image seems fine, but sometimes things are still evolving. So this release 0.10 was released last Monday. And this particular small thing will be in 0.10.1, which will be available in less than 48 hours. By Friday morning, you're going to see this addressed. I want to highlight this just as a difference, but also to see the great effort which this Spring Native team is putting to address these things as quickly as possible and to identify any problem which could arise along the way. So when we come back, we looked at initialization, we looked at dynamic features. Let's quickly look at features incompatible with the closed world optimization. One is the security manager. So because some features are not yet supported in the closed world optimization. So security manager was deprecated in Java 17, and the Graal and the Oracle team announced that Java 18, it will have it removed altogether. It was not recommended for some time. Invoke dynamic bytecode and method handlers are also incompatible. So because invoke dynamic could introduce calls at runtime or change the invoke method. And let's not forget that in closed world assumptions, all the methods that are called and their call sites must be known. So we cannot allow any kind of changes. There is an exception to this rule. Use cases generated by the Java compiler. For example, string concatenations and Java Lambda expressions, they're supported because they do not change the called method at image runtime. Furthermore, they're understood by native image right away, and they will speed up our application and our build process because they're easily understood. Now, features which are operating differently in native images. When we looked at initialization and we compared build versus runtime, we could see that native image implements some features in a different way than the hotspot VM. So class initializer, so files are loaded at runtime, might be in a different, at build time might be in a different place as runtime. Running threads cannot be loaded, cannot be stored. Finalizers, yes, they're deprecated since Java 9, and they were already recommended to be replaced with weak references or reference queues. Now, threads, native images do not implement deprecated methods such as thread.stop. Unsafe memory access, and last is debugging and monitoring. You have to use native debugging and monitoring tools. Now, the last part of our discussion is let's discuss a few best practices. So let's discuss a few best practices for native friendly Spring, and we'll end up with one more example of how we think as enterprise developers of sharing code. If we shared code, we want to also share hints because we're building native applications. And we also want to see how we can extend these hints when we build native images. If we're end users, we are usually getting close to the seamless transition. However, we might be building frameworks, or we might have code which we transition, and we have to be aware of them and what we could do. So keep these in mind when you change code to become more native friendly. It's generally a good idea to avoid CGLib proxies, like the class proxies we saw in the previous sample. They're fine to be used at configuration annotated classes, and we need to be also aware that bean annotated methods do not support cross bean invocations because they require a CGLib proxy created at runtime. When you write code, please try to think that or strive to write code common to both JVM and native. Rather than using Spring native specific codes, Graal has its own libraries, and you can do that too if you just build Graal apps. But if you're using Spring native on top, things like a native detector, which allows us to check, am I right now in a native image or not, should be avoided. Now, is this a hard and fast rule? And it's like in architecture, many times things are not black and white, they're gray, something in the middle. If we write frameworks, maybe it's important for us to make this distinction. But when we write application, which will go to production, we don't want to write this dependent code because we want to write one code base, which should go seamlessly to production. Now, favor functional approaches like lambdas and method references instead of reflection wherever possible. And I'll give you a glimpse of the upcoming 0.11, which will be probably released around Spring 1 at the beginning of September. So these constructs for functional approaches are automatically understood by the native image static analysis. And if we can, move reflection to build time wherever possible. In static blocks, fields of a class initialized at build time, in an AOT transformation. But last thing, please avoid complex initializers. They could lead to security vulnerabilities and deadlocks in the JVM. Where could this happen? This could happen if we look at our initialization problems. We have one sample here, which we did not look at. Let's say we write a shared utility where we move this random generator and we read some properties and get different random numbers. If we write this in a library, we write it, but whoever uses the library might not know about it, or might just simply see the library. I see this random generator. Oh, it has been shared by my organization or by my line of business. How about I'm going to use it? And then this could create a problem. As we compose and have more complex initializers, that could create a problem for us. Now, if we look at samples, how can we actually improve our code? So let me bring up a troubleshooting application. I used this application for a bit just to try different features out. And this class declares a number of hints. Some are JDK hints, some are loading a UID. One is our char set class, and we have the initialization hint, serialization, and so on. So we run this bean. This will have a bear which talks and eats. My daughter was a big fan of bears, as well as the color green. That's what I'm using for, I use green for my background. And we run this application. So when we run this, this is actually nice. We can see this, great. It will tell us that I've started this app. I assigned an ID to this bear. I loaded the char set. I intercepted talk. I didn't intercept eat because the bear must have been eating. Then I serialized the ID. But should I actually now write all these hints over and over again? How about I move them into a set of shared hints? So Spring Native allows us to extend hints. As long as we extend the native configuration, we can build a separate library and we build a class, and we can annotate this class with all the hints we had before. If we do so, we can reuse that library in many applications. And for an enterprise type of development, think like we have a monolith, we break it into 10, 20 services. Now we're going to run this. What should we do? Why don't we use these shared hints? So one is just reusing hints in a library, but we have another option. We have the option of programmatically adding hints and creating hints. I could add here via reflection a number of specific classes in my library. I don't know. I worked on a previous library before called Light4j. Maybe I want to leverage that one. So the alternative, where you could see this right away, where we had our initialization hint, yes, we could add all char sets. But how should we make our application aware? Well, we're going to create dynamically a number of hints where we add a number of options like enable security services, HTTPS, HTTP, add char sets, or so on. The moment we do this, our application could now be simplified. How can it be simplified? Well, if we look at it, suddenly you do not see here any hint, and the application would run fine. So it would run fine. So this is great. So it can run with these shared hints, and this is great. But how did it actually run? So in the POM file to the AOT plugin, we can extend that and we could provide it some more hints. So it will take the hints which it understands natively from, well, I use natively for native, which it understands as configured in the Spring Native project, but we can add also our own if we choose to do so. So we have here full flexibility. Always keep in mind that this is something which might not be obvious, but it is something very handy for us. And last thing, a little peek into 0.11, functional bean registration. This will be massive improvement in terms of size and in terms of speed. We know our regular annotation, whatever we can annotate with @bean in configuration classes, but how about if we would register the bean in a functional way? How if we would do this? This would be right away understood by the native image, and it would be like, great, we can do this. Now, if you have an application and you have built your Spring applications for a long time using these annotations, do not despair, you don't have to change them. Think about it for the future that you might wish to do so. But Spring Native will add functional bean registration, and it will do, like it does for all the other configuration, the heavy lifting for you, and it will generate the functional configuration. Very important for us, and this is going to be the major feature of the upcoming release. To recap, we saw how we build apps, and we would want to have a seamless transition from JVM-based apps to native images. But regardless of how we would build our application, regardless of the framework we would have to do, we still have to understand what the major category, major aspects which are important to us for native image compatibility and optimization. So again, class initializers, class metadata features, so initialization, dynamic features, but also be aware of incompatible features with closed world optimization and features which might operate differently in a native image. We started from how can any of them trip us up? So now we can see for each one, and we have examples for it. So with this, I want to thank you for watching this presentation. Here are some links. Peter will share them, and you can, if you want, you can screenshot this screen. You can reach out. You can find me on Twitter, and there is a full set of examples here. These examples have been provided as part of a large workshop at KubeCon Plus at the end of May, and they're still running with 0.9.2. 0.10 came out last Monday, and the temptation was too high to show you class proxies and native tests, because they're very important for us to know about. In the next few days, this repository will migrate to 0.10. Actually, it will migrate to 0.10.1 after this weekend, now that this release comes up. And when you go through it, consider this as a mini reference. The samples, you will find some of how we would solve it directly with Graal. Same as with class initialization, same as with looking at the dashboard with the same samples. And also how you would do it with Spring Native. And for each one, they're documented where you find the samples, how you would go through each one. Don't get lost. Because in order to understand all these differences and what can trip us up, we want to also have always like a point of reference and understanding each one of them. But we want to do it on our time without always dabbling around and trying to find some information. It took me some time to understand many of these or troubleshooting some of these problems over the last few months. But take each one of them as a learning opportunity, because troubleshooting why the class proxy, what the difference was, and then comparing the classes and looking at them gave me a whole opportunity to understand how they work. So it was time well invested. I want to make this a little bit easier for you. Start from these teachings and look at them into the future. So think always what's happening under the hood. And as much as we would like to have things moving seamless, we should always understand that in languages, in a language like Java, with dynamic features and with possibilities of initializing classes in different ways, we also can have the possibility of running into different type of issues. So thank you again. I'm going to stop sharing this screen if I find my Zoom button. And
great, Dan, thank you.
Thank you for inviting me.
We've got some questions teed up in the Zoom chat, a number of them. So we can just start running down the list if you like.
Yeah. Can we run application build in applications like JBoss and so on? The answer is no. This was not meant for running an application servers. Application servers have a different approach. You set up Java, you set up the application server and run this. Peter and I worked at BEA and we were building WebLogic, and no, this is not for that particular world. This is for building applications. You don't necessarily have to run them in Kubernetes. You might just build your Docker image, but you might as well build a native application. That's a native image, a lightweight container containing a native image. We saw our pet clinic put into a container. Another question, can you build a Docker image and use from scratch? Yes, you can. So there is an approach for this. So Spring Native gives you by definition, and let's pick up any sample. Let's pick up any sample. Where is pick up? Where is my it leverages cloud native build packs. Cloud native build packs are part of CNCF. They the project was initiated by Heroku. The packages, which the implementation is called Paketo, and the team building the build packs, which will help you transform source into a lightweight container, are built in parallel for Java for OpenJDK as well for native images. So we use native build packs. I didn't go into how we start from start.spring.io and how we would build it. So the native images will build an optimal image for you, and you saw that pet clinic at 17 megs. If you were to answer a question about Scratch, so if you are to want to run it via let me bring this other workshop up. I have a larger image here. Let me just find this particular image for you. Give me 1 second. I will show you how you can build this. Okay, right here. So share, where's this one? So if we share my screen, you can build a Docker image if you want to pick straight up, build it with GraalVM directly. You can build a static native image for images built directly with Graal. If you, and I'm referring just because you want to use Scratch. And these are statically linked binaries, which can be used without any additional library dependencies. They're good for using a Docker container. And mostly static, where you link everything but libc. But if we look at this Docker file, it is quite verbose. And cloud native build packs do not require the use of Docker files. So it will automatically, you give it the source code that gives you the Docker image. But if you choose to do so, let's think about this. The native image is built for the OS and the host on which we're going to run. So we have to build this quite verbose file. This file was actually shared the first time by James Ward, who worked for Google. And he was looking at exploring this. And he was saying, well, you take your distribution of Java 11 and Graal 21.0. This was built like 3 months ago. Then you have to install the native image. I cannot make this larger. Then you have to install all the components, build your application, build your application, run the native image. So you build this in a container. Once you have your application, and this is a Hello workshop, which I used at QCon and some other workshops, now I have this application. So with this application, I can take an image from scratch and build this, and now build a container. It will require you some additional effort if you want to use this particular one. I would strongly recommend that you use build packs, because sometimes you can improve your user experience not by making the progress, making something better. You can just remove it altogether. So if I don't need Docker files, why would I consider building this, especially if I'm going to build en masse? GraalVM, yes, it's not a bug, it's an optimization. The version of GraalVM is 21.1, 21.2, which will be released, to my knowledge, July 20th, is going to address this optimization. That is correct. And this will be improved. It's not a Spring native thing. It is a Spring, it is a GraalVM. Please also be aware that I'm using Java 11 for the following reason. Right now, Graal supports 8 and 11 because these are the last 2 long-term support releases from for the JDK. In September, when 17 LTS will be released, please be aware that Graal will not support Java 8. So there will be only Java 11 and 17 of Graal available. Of course, there's a 16, but as long-term support. So think about this, that, I mean, there's no real reason why you should not take a Java 8 application and compile it with 11 at this time. But think about this, that as of September, there's not going to be Java 8 support. But yes, Matt, this is Java 11. It will require more optimization. So if you want to identify which class needs to be built at build time, in your example, yes, you can do that when you run your application. If you want to run it in your application, you can run. Let me see if I have this open. It's not in this one. There is a flag called print class initialization. You can run it straight from the native image, or you can add it as a plus print initialization in your application, and it will build it for you. Let me see if maybe I don't have it here. No, I don't have it in this particular sum I have in the workshop. If you run it, it will give you which class you would run. But you can also see in all the applications we ran, when we ran that class initialization in native image.properties, you will see what we have specified to build there. But the print class initialization would give us a hint. Well, this was initialized there, and this was initialized at build time or at runtime. Now, runtime
but more specifically, it won't necessarily tell you which class is the problem per se, as far as what needs to be initialized at build time, but it'll just give you more information. Is that what that's going to help with?
It will tell you where it was initialized. So now it is your choice. What I would suggest that, because if you're using Spring Native like I do, I like to look into under the hood so that I understand the mechanism. But if you use Spring Native, I would recommend, and that's in general, run it and let everything be built at runtime. Let Spring Native make these decisions. Then maybe look at your dashboard, the Graal dashboard, and then maybe you can see, for example, that Jackson sample. Maybe we want to make such sample, but again, you do it with care. So you let the system optimize things for you. So runtime initialization is the default at startup, and then Spring Native will decide what to do. For example, enum, if I have enum, my first, my second, my third object, and it carries value 1, 2, and 3, that enum is a perfect sample, and Spring Native will put that build time, because now I know about this. So whatever you could move at build time, if you could register, if you were write your magic application, you would register in one, I don't know, I'm just saying, in one big static initializer block, you register all your classes, your application will be as fast as possible. Because it will, whatever is in the image heap, that image heap is part of your native image. If it's part of your native image, it gets loaded right away at application startup. Whatever is there, it's available to you right away. That image heap does not change. What is in the image, this is how it stays. So last question here was whether a static method will face the same issue by returning the same value. So a static method, well, depends what you would return from it. If you think about it, that random number, I put that in a final. By putting that in a final, optimization was that, okay, this is fantastic. I can load this this shared utility and build this at initialize it at build time. So by asking this, I'm thinking, well, I've actually done something great, but actually I might have not, and I've created inadvertently some problem. That's why I'm saying maybe we can learn of how to write maybe better code, revisit code from the past, or look at new things, or you see threads could not be written. Or if I'm leaking my user home from the build machine, and I'm not my personal Mac here, but think about it, about some build machine, and then I have some relative folders, and I might have loaded other things. That is always something which we should care about. So it's an interesting topic, and it's and there are things which are evolving very fast. Now, would you have to provide some hints for some of your application as you're building it, especially if you're building different frameworks or have shared frameworks within an organization or open source? This is where you have to be careful. If you require additional hints, and you could see, you can build a shared hint out of existing hints or programmatically build them. The team is welcoming any contribution. Please be aware that around October, I don't want to put a date, the GraalVM team will open a new project where they will allow some contributions for shared configuration. By making that available, it will be available across other frameworks, across your own projects, and so on. For the time being, then the Spring team focuses on Spring projects, common use projects, you see those. And for different edge cases, for things which are missing, either you build a shared hint library and use it, or you do that and send a PR, and the team will be very happy to merge it. Any contribution, as it always is with open source, is welcome and encouraged.
Cool. I think that's the question queue, right? Anyone else? Yeah, let's let Dan get a drink of water here. Yeah, no problem, Matt. Yeah.
Happy to answer your questions, and feel free, if you have any other questions, feel free to ping me. Feel free to look at this repository. At Spring 1, we will do 4 different workshops. 2 will be self-paced, 2 will be instructor-led. Some will be more of an introduction, think like a level 100, 150, and 1 will be more advancing. I'm hoping that I can show you more features, things which, that's a little sample of showing the differences, has a short lifespan. 2 days from now, I can't really show you, or I can just show it to you as things improve. So it's a fast-paced environment, and please follow it.